Hi, and welcome to Reducing Latency for Live Over-the-Top Video Delivery. I'm your presenter, Ernest Russell, Technical Product Marketing Manager for Limelight. On today's agenda, we'll talk about what is latency and why is latency important, low latency use cases, major factors that influence live stream latency, tuning HTTP chunk sizes, chunk CMAT, and Limelight real-time streaming. So what is latency and why is latency important? Latency is the delay that it takes for video to process and propagate through the network to the viewer's device. For live over-the-top delivery, latency is the time it takes for live video from the camera to be encoded and distributed through the network to an online video player. That video player can be embedded on a website or a mobile app. So why is latency important? OTT requirements vary by content. For example, live events like the Super Bowl, World Cup, or Kentucky Derby may have an added value by having ultra-low latency, while other VOD content like movies or TV shows may not require low or ultra-low latency. Low latency enables interactivity like voting, auctions, and wagering. And also the integration of live data and social media requires low latency. Overall, viewers want to enjoy the same viewing experience regardless of their device and regardless of their location. Let's take a look at some low latency use cases. The first would be online gambling, where when we use low latency, we have the increased opportunity for wagers and the decreased opportunity for fraud. We boost productivity by speeding up online play. More hands usually means more revenue. The second case would be live sports and events, where we can create value-added experiences, and also with low latency, we can add wagers, statistics, camera angle changes, and add additional opportunities to monetize live video outside of a region. Also, there's the case of spoilers. We've all been in a restaurant or a bar watching a game or a match, and someone watching on a different platform cheers before you see the goal or touchdown. Low latency can reduce the occurrence of these spoilers. Then we have gambling and esports, where greater interaction with competition and also being able to broadcast in low latency creates a more immersive experience. And finally, meetings and events, where we need to reach a large number of remote attendees and interact and collaborate between multiple locations. Now here we'll take a look at the streaming latency continuum and some of the average streaming latencies for different streaming protocols. The first on the left here being typical HLS latency. Typical HLS latency can be between 60 and 30 seconds on average, while other typical HTTP adaptive streaming technologies, the latency can be around 30 seconds, while cable TV latency is 5 to 6 seconds. So once we get below cable TV latency, we consider that low latency, under 5 seconds, and then ultra low latency when we get a second or below. And also finally, real-time latency when we get into milliseconds of latency. So what are some of the major factors that influence latency? One would be the video protocol. Another would be the video chunk size, and also the video player buffer. So let's take a look at live streaming using TCP/IP. But first, we'll review some history of internet live streaming. The internet was not originally designed to deliver video. HTTP live streaming protocols, they emerged as a way to deliver video files over the internet by breaking the streams into a sequence of small HTTP-based video chunks. By using HTTP transactions, HTTP live streaming can traverse firewalls and use standard web servers to cache and deliver video streams and take advantage of content delivery networks to scale delivery. And here's how live streaming works with HLS, Dash, MSS, and HDS. Live video comes from a camera into the encoder. The encoder creates a manifest and video segments. The manifest describes those media segments, including timing, URL, video resolution, and bit rates for adaptive bitrate. The advantages of using a manifest is that we can manipulate that manifest to personalize content, apply regional audio or closed captions, change playback order, or adaptive bitrate. So for ADR segments, we would have different resolutions and bit rates in the manifest, and video selection can be switched based on network conditions, device type, and user preference. The segments are sent to an online video player, and most video players need to buffer 3 video segments before starting playback. So what can we do to reduce latency for live over-the-top streaming? One thing we can do is reduce the HTTP chunk size. Another would be using chunk CMAT encoding. And third, use WebRTC over UDP. And I'll talk about those in more detail. Tuning HTTP chunk sizes. So what is chunk size tuning? Chunk size tuning reduces the video segment length for encoded media. When our encoder creates chunk sizes, let's say they're created in 10-second chunks. The player will need to buffer 3 video segments before playback begins. So if we have 3 chunks that are 10 seconds each, we have 30 seconds of video that must be buffered before the player can begin playback. Then in the example below, we also have 3 video segments, but the length has been reduced to 6 seconds each. What that allows is instead of 30 seconds of video to be buffered, we only have to buffer 18 seconds of video before our player can begin playback. There's no universal setting for chunk sizes. Over-reducing chunk size can actually introduce buffering from the player. So each workflow should be tested accordingly. Now here we have our MMD Live. MMD Live is Limelight's solution for live multimedia device delivery. MMD Live takes an RTMP or MP4 input and transforms that input on the fly to various HTTP streaming protocols that are needed to deliver to mobile and OTT devices, including HLS, HDS, MSS, and MPEG-Dash. With MMD Live, chunk sizes are configurable, and with chunk size tuning, we've been able to achieve latency as low as 6 seconds. It supports all HTTP chunk sizes and streaming formats, and also provides global delivery to all of our edges with the same effective latency. So our multimedia device delivery also supports DRM on the fly and has the built-in security features that you expect to protect your content from unauthorized views. Also, MMD Live is a great choice for low latency delivery, especially when there's not the need for ultra-low or real-time latency or interactivity. MMD Live can achieve latency as low as 6 seconds. And next we have CMAT. So what is CMAT chunk encoding? And why was it developed? What challenge is it trying to solve? Well, CMAT is Common Media Application Framework, and it was an effort to move towards a common low latency file format. HLS and MPEG-Dash are the 2 dominant HTTP streaming formats in use today. HLS and Dash have traditionally used different methods of containerizing video and audio. By using a common framework to store the files, this means that content owners wanting to deliver to various tablets, computers, phones, and OTT devices out there can store and package files once instead of having two separate sets, each holding the same video and audio data. And the benefits of CMAF are, one, it reduces end-to-end latency. Media can be accessed by HLS and dash manifest simultaneously, and so it simplifies the workflow by processing and storing one set of files, therefore reducing costs for delivering dash and HLS. And how it works is CMAF creates microchunks or video fragments that enable segment delivery in small fragments before the full video segment is downloaded. So decoding and playback of these video segments can start before the complete segment is received. CMAF outputs smaller chunks that can be processed by the decoder faster. Here we'll take a look at CMAF encoding in more detail. At the top here, we have a non-CMAF chunk video fragment. It starts with a movie fragment box, or MOV, that contains timing and duration for each video sample to follow in the movie data box, or MDAT. After the complete segment is chunked, then the video samples are output from the encoder, and the decoder is able to start the decode. As you can see here, the complete segment must be encoded and written before playback can begin. At the bottom here, we have a CMAF chunked encoded segment, where additional moves have been injected to describe smaller chunks of video. This allows the decoder to start playing back before the entire video segment is received. There's a separate header that's required to initiate or initialize the CMAF chunk streaming playback. So let's take a look at some of the requirements of CMAF. So for CMAF, there are a few things that must come together in order to achieve a drop in latency. One is the encoder must create smaller micro chunks or video fragments. Along with that, the manifest must be able to be updated to carry the extended metadata to describe the new content in smaller chunks or video fragments. Also, the CDN must support chunk video transfer, or HTTP 1.1. And then finally, the player. The video player must be dynamic enough to read the manifest and adjust its buffer accordingly. When all of these things come together, a latency of 3 to 4 seconds have been achieved with CMAF. So next, let's talk about WebRTC-based streaming. WebRTC, or Web Real-Time Communications, is an open source project for browser and mobile application communication. WebRTC uses UDP instead of TCP/IP to broadcast streams. So streams don't need to be chunked by the encoder before broadcasting. With WebRTC, we're able to achieve sub-second latency anywhere in the world. And part of that is because no video chunking is required. Also, we've been able to achieve global scale with a solution that's supported by standard web browsers without the need for special plugins. Also, WebRTC has a live data channel enabling interactive online live experiences. So let's take a look at Limelight real-time streaming and how we use WebRTC. Limelight real-time streaming uses our private managed network to broadcast WebRTC video to our WebRTC edge nodes. When a viewer requests a stream, our stream manager delivers the stream from the edge node closest to the viewer. On the left here, we see that we have an RTMP input, which is very common for both consumer and professional grade encoders. That RTMP input is converted to WebRTC and broadcast to our edge nodes globally. Again, WebRTC is broadcast over UDP. If there's a case where UDP is blocked, Limelight real-time streaming can fall back to WebRTC delivery over TCP/IP. So Limelight real-time streaming has all the security features that you've come to expect from a streaming solution, including IP white and blacklisting, blocking content by region, and tokenization with our Media Vault service. Limelight not only allows for sub-second ultra-low latency, but also with the data channel in WebRTC, it allows us to add real-time interactivity for a next-level experience. In summary, HTTP streaming live protocols have a latency penalty when the encoder has to create video chunks. When low or ultra-low streaming latency is required, consider chunk size tuning or WebRTC streaming technologies. Chunk size tuning can increase performance, reducing latency caused by the player buffer. And WebRTC does not require video chunking and buffering required by other chunk streaming methods. And latency, it depends. It depends on whether it's a live event, VOD, movies, TV shows. So your latency requirements really depend on the content that you're delivering. MMD Live supports all chunk formats and persistent connections, providing a source-to-viewer latency as low as 6 seconds. While if you have the need for ultra-low latency, Limelight real-time streaming provides sub-second live streams, no chunking required. Ultra-low latency and data sharing provide the ultimate interactive live viewing experience. So talk to Limelight Network today about which streaming solution works for you. You can be reached by email, Twitter, LinkedIn, or Facebook. Thanks for joining us.